So last time we were talking about, well, we started talking about fields, and so we talked about the definition of a field. We talked about some examples, like the basic examples, the rational numbers, FP, the complex numbers, real numbers, and then we sort of went and saw some more exotic examples, and sort of saw that there are some other general ways you could sort of produce fields. So like in particular, taking just an arbitrary commutative ring, you take a prime ideal, and then you sort of take R mod P, that's now an integral domain, you take the fraction field of that, just to sort of enlighten and enrich our world of sort of what we're dealing with here. And then we sort of started talking about, so I don't think I called it this, but the book calls it this, so I'd better at least say it, the prime subfield of any field. So if you're in characteristic 0, the prime subfield is sort of this canonical copy of the rational numbers that gets embedded. And if you're characteristic P, it's FP, the field with P elements, or Z mod PZ, sort of living over it. So any field is built up, like starting from its prime field. So either built up from the rational numbers or built up from FP. And we started to talk a little bit about what that building up process could look like. So we're talking about sort of, you have a field extension, you sort of have one field containing another field, but sort of you look at it sort of the other way, you sort of starting with the smaller field and you're building the bigger field. And we talked about sort of, in particular, what happens when you just take a single element and add it. And that sort of had some dichotomy. Your element could either be transcendental, in which case it looked like sort of you were just getting some field that was sort of living, like the smallest subfield containing that element is just abstractly isomorphic to a field of rational functions in a single variable. Sort of had, even though that element could be anything, like somehow the just abstract algebraic structure is the same as the field of rational elements. And then sort of the other alternative was that the element was algebraic, which meant it's a root of some polynomial over the base field. And in that case, you again sort of have a very specific structure, just you're sort of the quotient of a polynomial ring by the minimal polynomial. And so we discussed this, and we're going to keep on building on these ideas today. I want to start by just generalizing one definition from last time because it'll be useful to do so. So, okay, so if L over K is an extension of field, so field extension, and then I have alpha 1, sort of alpha n elements of L, then if I write K parentheses alpha 1 to alpha n, then this is just the smallest subfield of L containing all of these elements and K. In particular, it's sort of useful to think of sort of adding them one at a time. So if I take K and if I look at the smallest subfield containing sort of alpha 1 to alpha 2, alpha n, well, in particular, that contains the smallest subfield that contains alpha 1. And then I sort of get up to this guy by just sort of also taking alpha 2 to alpha n. That's sort of K alpha 1, alpha 2. I mean, somehow and so on. So you can sort of think, and if you're doing this, you can sort of think about sort of adding in all of these elements and taking the smallest subfield as sort of adding in one at a time. If you sort of have a finite list. And there's also, there are times where it's useful, and probably not so much in this class, but sort of more generally, to think even more generally. So if you have S is just a set, so it's just going to be a set of indices, and then, or let me call it I's for indices. If I is a set, and alpha I, L for I contain I, so you have sort of some collection of elements indexed by this set I, then you can also define K sort of, you can sort of consider the smallest subfield that contains alpha I for all of these for all of these possibly infinite now set of elements. So you can take the smallest subfield sort of containing all these things, and this still makes sense as well. So we're mostly in. There are various reasons where, and we're basically always only going to be interested in finitely sort of things, field extensions. Okay, let me not say that. For us, the most important thing is going to be sort of finitely generated field extensions, and then even really sort of just field extensions you get by just adding a single element. And it turns out sort of you can get quite a bit by adding a single element. Sort of most field extensions that sort of come up in like basic algebra, sort of you can get by adding a single element. So this is the so-called primitive element theorem. So you actually sort of have to work hard to sort of write down a finite extension that isn't obtained by just adding a single element. And having these more general notions is sort of will be useful at various times. So let me, in particular, sort of give a name. So if L is equal to sort of K alpha 1 and alpha n, so this just means, I mean, L over K is some extension still, and I have these sort of n elements of L. And I'm just saying sort of, if I take a field that contains K and those n elements, then actually sort of, it's the whole thing. Like there's sort of no smaller field that contains these things. Then we say L is finitely generated. So, I mean, this is, we'll see in a moment, then this is related to this notion we had before of being a finite, of degree. So let me sort of write this other definition. So if the degree is less than infinity, we say L is a finite extension. So I probably didn't actually write this down last time, so it'd be good if I'm saying it now. And so I just want to point out, these are two different ideas. So being finitely generated is not the same as being a finite extension, although we'll see in a moment that there's sort of the obvious difficulty, or the obvious difference is the only difference. So can someone tell me, can someone just give me an example of a field extension which is finitely generated but not a finite extension, in the sense that sort of this degree as a vector space, the dimension as a vector space is not finite? Okay, so someone posted in chat. So just an example. So if I take the field of rational functions in a single variable over K, this is not finitely generated, is not finite, but it is finitely generated. So here we again run into sort of this notational limbo where sort of this means the field of rational functions in the variable x, sort of over K. So just the quotient ring of the polynomial ring over K. But it turns out the reason this is sort of bad notation is because like X is also an element of this field, and like we have a subfield K parentheses X, sort of the smallest subfield containing X. But luckily, this field is generated by the element X, so it's okay. So this field is generated by a single element, just by X, but it's well, not so hard of an exercise to see that it's infinite dimensional. And there's a little bit of work to see this as an infinite dimensional as a vector space. If K is well, no, I guess maybe it's not any work ever. Right, so I mean, in particular, this contains the polynomial rings. Sorry, I was thinking it was a slightly different thing. I was thinking about sort of distinguishing accountable. So I was mixed up for a second because I was thinking about a different problem about distinguishing sort of countable dimension versus uncountable dimension. Here, it's very easily to see that this is not a finite extension. It's not finite as a vector space because this contains the polynomial ring, which is sort of has a countable basis just given by the monomials. Okay, but it is finitely generated. So, but it turns out this is essentially the only thing that can go wrong. Like, as long as a field extension, a finitely generated field that doesn't contain any transcendental elements will be a finite extension and sort of vice versa. So we'll make that precise in a moment. Okay, well, yeah, let's go ahead and make that precise now, actually, and then we'll come back to the other thing I was going to do. So, if an extension is algebraic, if every element of the sort of bigger field is algebraic over K. Okay, and so we say an extension is transcendental otherwise. So it's algebraic if every single element is algebraic over K, and it's transcendental if there's even one element that is transcendental over K. So recall saying an element is algebraic just meant that its minimal polynomial is not zero, like sort of that has a minimal polynomial. Okay, and so then the result is over K is finite. That recall means that that the degree is less than infinity, if and only if L over K is finitely generated and algebraic. So there's basically one sort of non-trivial thing that goes into this. There's one sort of interesting observation that goes into proving this. So let me say what that interesting observation is. So the main lemma is showing that if you have a finite extension, then it's in fact an algebraic extension. So, I mean, assuming this, you're sort of set. So then to prove the theorem, you just say, well, if L over K is finite, then in particular, it's algebraic. So this part is sort of check. And then, well, to see that's finally generated, sort of you just add elements one at a time. Like each time you add a new element, you're sort of at a minimum cutting down the dimension of sort of the extension by one. And even more than that, but so you can see that sort of every time you add an element, you're sort of cutting down the possible dimension. And so since the dimension is finite, sort of there's only sort of finite elements you can add in before you sort of just reach L itself. So that's sort of, once you have this lemma, sort of that direction is pretty easy. On the other hand, like going up is pretty easy. Going the other way is pretty easy because like if you're finally generating algebraic, well, that means sort of you can do this iterative thing that I said before. Like you sort of write K alpha 1 through alpha n, is sort of first you add alpha 1, then you add alpha 2, and so on. And then at each of these steps, you know, you're sort of just taking like a field, you're taking a polynomial ring mod f of x, where f of x is sort of some finite degree polynomial. And like that's easy to check, sort of that vector space is of the same dimension as the degree of your polynomial. So sort of you're sort of stacking up at each time. And then, well, I guess there's another lemma you need that I didn't state. So let me say the other main lemma. So if you have a tower of field extensions, then the degree of sort of the biggest extension, so m over k, is equal to the product of the degree of m over l times the degree of l over k. So you use that when you're showing the finally generated algebraic implies that the extension is finite because you sort of break it up into some chain of extensions where you know sort of each one of these extensions is finite, and then you just use that sort of the total degree is just the multiplication. You're sort of multiplying together these n finite numbers. Right, so I think in the interest of time, I will, and that's all I'm going to say about the proof of the theorem once you have these lemmas. So you can go back and sort of reason that out more carefully on your own if you'd like. I'm going to go over the proof of this main lemma because that's, I mean, it's not a hard proof, but like it's a proof that like if you don't, and it's sort of the idea is very fundamental, so it's a proof that's sort of good to write down and just see carefully. And then this other main lemma, like this is basically just a linear algebra argument. Like you sort of start with a basis of m over l, and then sort of like take a basis of l over k, and then sort of just combine that in the natural way, and you'll get sort of a basis for m over k. And you don't even, and that's somehow even easier than that because like to prove something is finite dimensional, you don't even need a basis. You just need a spanning set. So you don't even have to check, or well, I wanted to get the product, so you do need to check the basis. If you only wanted the part that you needed sort of for this theorem, it's even simpler than that because if you win, you just have to check that you got a spanning set. So you just have to check this sort of L over K finite and M over L finite implied M over K was finite. But this identity will be useful. But anyway, this is just sort of a linear algebra exercise. Okay, so the proof of this main lemma. Okay, well, so we want, and we're assuming L over K is finite. We want to show L over K is algebraic. That means we have to show every element of L is algebraic over K. So let me just take alpha contained in L, and then I'm going to look at the elements. And let me write D for the degree. I'm going to look at the elements 1, alpha squared, alpha cubed, alpha to the D. This is D plus 1 vectors in D-dimensional space. Okay, so there is a non-trivial linear dependence, which says sort of A1 times 1 plus A2 times alpha, or sorry, let me say A0 times 1 plus A1 times alpha plus A2 times alpha squared plus AD times alpha to D. So I guess this one is also just an exercise in linear algebra. So I have D plus 1 vectors in this sort of D-dimensional vector space. That means there's a non-trivial linear dependence where sort of the A, I are all elements of K because this is a D-dimensional K vector space. Okay, well, this is a polynomial. Okay, so if I write f of x is equal to A0 plus A1x plus A2x squared plus so on, AD x to the D. This is a non-zero polynomial. So the fact this is a non-zero polynomial is just the fact that this is a non-trivial linear independence. With coefficients in K. And F of alpha is equal to 0. I mean, sorry, this was supposed to say this is equal to 0. So this non-trivial linear dependence is just literally the statement that if I take this polynomial f and I evaluate it alpha, I get 0. So, and that means, and this is exactly what it means for an element to be algebraic. Element is algebraic if there's some non-zero, if it's a root of some non-zero polynomial. Okay, so alpha is algebraic. Okay, so good. So this is, let me go back just to this statement and hammer it one more time. So the statement of the theorem was that being finite, so being a finite extension, which means the degree is finite, so that means the dimension as a vector, K vector space is finite, is equivalent to being finitely generated and having, and sort of finitely generated and algebraic. So that's the statement. And this sort of, in some sense, this explains why so much of what we're about to do in the rest of the course is study finite extensions. I mean, like if you first say we're going to study finite extensions, you say those are the extensions where this degree is, where like the dimension as a vector space is less than infinity. Like, and if you had never seen field theory before, like you might guess that that was like a rare thing, like that sort of you didn't see those very often. Like it's a pretty strong condition to say sort of the dimension of this vector space is less than infinity. Like, and if you start thinking about your first examples, like rational functions, like you see like it isn't satisfied in these first and like rational functions. Like, and like it's easy to write down examples where this isn't true. But somehow, I mean, a lot of the thing that's interesting about field theory is sort of studying roots of polynomials and like studying sort of how you can sort of understand existence, non-existent roots of polynomials and like sort of the structure of polynomials by using field theory. And so that's all sort of about algebraic extensions. And then like if you know every finitely generated algebraic extension is a finite extension, like sort of that makes them sort of, well, that sort of makes it more plausible that this is sort of an interesting world to work in. And then sort of, well, being able to go in the other direction is sort of a very powerful tool sometimes. So in this main lemma, in this idea that if L over K is finite, then L over K is algebraic, like this is something we'll use again and again. And it's sort of, then it's a simple linear dependence argument, but this is a very powerful statement. Okay, so next topic. I mean, why are we talking about field theory? Well, we're talking about field theory because we're about to talk about Galois theory. So why are we going to talk about Galois theory? Well, because Galois theory is something interesting, because Galois theory is telling us about a basic problem in math. Like, Galois theory gives you a way of understanding the structure of roots of polynomials. It gives you a way to understand like when a polynomial has a root. It gives you a way to understand when you can find the roots of a polynomial in a certain way. Like this is sort of, I mean, somehow people have known forever that this is intrinsically important. Like, I mean, this was like, I don't know, one of these people, and you've probably heard these stories about like Italian math competitions to be a tenured professor, and like sort of you can challenge someone, and like like this is like the origin story of like the quartic equation or something. Is sort of like someone like, and sort of you could sort of, if you could solve a quartic equation, you could sort of get like whatever tenured professorship you want. You could challenge for it, and like no one would be able to solve your problems, and then sort of you get it. You like, it didn't matter if you knew any other math. I mean somehow like and that's basically like how it should be, because I mean it's like it is intrinsically interesting to be able to solve equations. Like this is why we care about math, at least sort of like, math you set up equations and then you solve them. Like this is sort of where math comes up, like when you're balancing your checkbook, like sort of like this is where math comes into like biology and things like, and you want to like at a base level, you just sort of want to like set up some equations describing some system, and then you want to solve those equations so you know what the answer is. Like finding roots of polynomials is sort of a fundamental question. And it's not obvious that, I think often an abstract algebra course is sort of taught in the way where it's sort of supposed to be obvious that field theory, like so some of this like assumption that it's obvious that field theory is useful for this, but I don't think this is really true. Like it's not obvious to me before like having developed field theory and like developed Galois theory that sort of studying fields should have anything to do with solving polynomials. But it turns out it does, and like in the following construction is sort of maybe like the main reason it has something to do with it at all, which is sort of if you have a field K and F is an extension of K, or so F is a polynomial, so a non-constant polynomial, over K, so an element of K of X, then there exists, I guess this is a theorem or a lemma, a extension L over K such that F has a root in L. So, and this is somehow the meat of it. And it's because like if you start with a polynomial you don't know how to solve it, you can always find some place where you can solve it that is also a field. And sort of doing this involves an extension. So this is sort of in particular how field extensions sort of show up in the problem of writing, sort of solving polynomials and writing roots of polynomials. Okay, so proof. And so the advantages of like having, so there are a lot of advantages. And by the way, this is something new this year, the way our algebra sort of content is split up between the 2 semesters, and it's like maybe a bit unusual to have like all of the ring and module theory before any group theory, and sort of the course setup. But like this is an example of like where that all pays off. Because like this is, and I don't have to explain anything to you here, and you already know because we've already done it, and like it's just a basic ring theoretic thing. Like, okay, let me say it this way. So, well, K of X is a sort of PID. So let me take or even just a UFD. So let me take an irreducible factor. Let me not use more than I need. G of X of F of X. So I know in any UFD, I can sort of factor things. And so I can take an irreducible polynomial dividing my polynomial F. And then K of X mod G of X is a field. So here, I guess I'm using that. Okay, I'll go back to PID. And here I'm using this is a PID to see that when I mod up an irreducible, I get a field. And good. And so, and the claim, so let me call this L, the claim. So if I write X bar for the image of X in L, then sort of X bar is a root of F. So in this sort of low, subtly in F of X was sort of a priori a polynomial of coefficients in K, but I can also sort of think of it as a polynomial in coefficients. And so I better, X bar is probably, yeah, this is one of those places where you can get yourself really confused. So let me use the variable y for defining L. Because I mean, I'm still going to have this polynomial in play. Like I still have this polynomial f with coefficients, so where the variable is x, and so I can think of that as being a polynomial with coefficients in k brackets x, but I can also sort of think of it as being a polynomial in coefficients with L brackets x in this field extension. And then so I'm just saying sort of f of y bar equals 0 in L. So this is I need to check. But and let me just write sort of f is equal to f of x is g of x times h of x. And then sort of f of y bar is equal to g of y bar times h of y bar. Okay, and so obviously sort of suffices to show this is 0. But and this is sort of g of y bar. I mean, I think of L as being this field k of x mod, so k of y mod g of x mod g of y. Then g of y bar, like you can just write it down. So this is, yeah, I don't know how much detail to go into here. And so you can go into more detail if you want. Like if you're having trouble, if you're getting lost right now, or if you're like, if this computation seems confusing to you right now, like that is totally normal. And like the thing to do if this, what I'm about to say seems confusing, or you're still like not fully sure what's going on, it's like just write out sort of g of x as a polynomial of sort of coefficients. And sort of like write out the coefficients and then sort of substitute everything in, sort of check that. And this is just the same as saying g of y bar. This is, that just means, when I write this bar, I just mean sort of reduce mod g of y, like reduce mod the ideal and quotient by. So this is the definition of this bar notation is just g of y mod or g of y, which is equal to 0. And so in some of this sort of this tautological construction, and like when you sort of when you take this field sort of k of y mod g of y, like you're literally declaring here's a field where like y is a root of g. Like this is sort of how you're defining your field. Okay. Good. Let me sort of add. So that's sort of how you do this construction. There's also sort of a uniqueness statement. Which is if L1 over K and L2 over K are sort of two fields. Well, they're sort of two extensions of K. And you have sort of alpha in L1 and beta contained in L2. These are both roots of an irreducible polynomial. So up here, and I sort of, when I said this theorem, I just said if you start with any non-constant polynomial, you could always find an extension where there was a root. But then the way I did it is sort of, I just took some irreducible factor and found a root of that irreducible factor. And I mean, sort of there's not going to be really any relation. If I took two different irreducible factors, then there's not going to be sort of any relation between their roots. So this uniqueness statement is just about roots of irreducible polynomials. So then the fields, so let me say this, there's an isomorphism of extensions of K from K adjoint alpha, which recall is sort of living inside of this field L1 to K adjoint beta, which is living inside this other field L2. And like these are just two completely different fields. Like you should not, when you see, I mean, this is sort of a subtle point, but it's important. And when you see like this setup, I have two field extensions, L1 of K and L2 of K. What you shouldn't do is think that these are both living in the same extension. Like you should not think automatically there's some larger extension containing both L1 and L2. I mean, it's true that you can always arrange for this to be true, but it's not, I mean, actually it's not such a, like arranging for that to be true is not, it's you have to say something. Like it's not like there's certainly no uniqueness to a field containing L1 and L2, and there's sort of no like. I mean, the point is sort of there's no like biggest field containing K, which sort of contains all other fields that contain K. So if I just sort of give you two extensions of K, like there's no reason to think these are sort of contained in the same. Like there's some bigger extension that contains them both. Like, and I guess I'll just say this now because this is a common mistake I sort of see with the way people learn things. I mean, if I said this and you said, and your response was just take the compositum of these two extensions, like you can't take the compositum of two extensions unless they're already contained in sort of, unless you sort of already put them inside some bigger field. So compositum is only defined for subfields of some larger field. So it doesn't like, with what I've written here, it doesn't make sense to take the compositum of these two extensions. So, okay, but nonetheless, so this, what this uniqueness statement is saying is, if I sort of take some field where I do have a root for alpha, or where I do have a root for this irreducible polynomial f, and so I take two different fields where I have a root for this irreducible polynomial f, well, and those fields might be completely different fields, but if I just sort of look at the smallest field inside of each of them containing that root and containing K, then I can at least find an isomorphism between those two fields. I mean, the point, well, I mean, the point is, it's easy to check that both of these have to be isomorphic to K of X mod F of X. So here the map is X goes to beta, and here the map is sort of X goes to alpha. So these are sort of, you compose these two isomorphisms, you get an isomorphism in this way. And this is something we already basically saw, but let me just sort of, and there's, I mean, if you look at this, like you see that, if you look at this for a second, like there is a little bit, and you do have to say something. This isn't immediate from what we just said. The point is like, well, alpha has a minimal polynomial over K. That minimal polynomial is irreducible. On the other hand, like f is an irreducible polynomial such that f of alpha is equal to 0. So then f has to be that minimal polynomial. But yeah, you should, yeah. So what's left to say here is just sort of to make this, to just double check that sort of f really is the minimal polynomial of alpha and the minimal polynomial of beta. That just follows from the fact that f is irreducible and alpha is a root of f. Okay, good. And let me highlight and you should, there's, isomorphism is not unique, is not typically unique. But, and it is sort of explicit. But sort of, so what do I mean by that? I mean, well, there might be okay, so first I guess I should have said an isomorphism of extensions of K, that just means an isomorphism of fields, which sort of restricts the identity on K. So because these are both sort of extensions of K, that makes sense. And when I say this is not unique, I mean, well, this is just a subfield of L1. I mean, this is just a field and this is just a field, and there might be other isomorphisms of these two fields that are at identity on K. Nothing I've said sort of guarantees there's a unique isomorphism. On the other hand, like, what I mean, but here is an explicit sort of in terms of the extra data. Even though there's sort of not a unique isomorphism, sort of there is a unique isomorphism, like, and somehow we've described an explicit isomorphism in terms of extra information we've specified. So, and some of the point is, like, specifying the element alpha, which is a specific root of f, is specifying more information than just specifying this extension itself. Like, I mean, K adjoint alpha, there's no, like, any sub extension is like, and this extension of K is sort of generated by many different elements. Like, alpha is not the only element that generates this extension. So the fact that sort of I've in the data sort of pinned down some element alpha, sort of a root of f, that generates this extension, I think that's given me more information than sort of just this extension itself as a field extension. And sort of similarly for this beta, and then sort of I've used the fact that I've given a root of alpha here, a root of f here, and a root of f here, to then sort of give an isomorphism between these two sub extensions. So the right sentence is sort of, this is the sort of the unique isomorphism sending alpha to beta. So where could this go wrong? And so this, I mean, the issue is in this sub extension generated by one root might have other roots in it too. So just like we saw an example of this on your homework. So example, if I look at sort of Q, I add in sort of e to 2 pi I over 3. When this also contains e to 2 pi I over, minus e to 2 pi I over 3, which is just e to, it's the inverse of this, but these are both roots of x squared plus x plus 1. So, I mean, if I don't, I mean, somehow, and this is the same thing we talked, and we did the same example with I instead of e to 2 pi I over 3 last time. And just the point is, like, there are two different isomorphisms from this field to sort of Q. So there are two different isomorphisms. I can send x to e to the 2 pi I over 3, or I can send x to e to the minus 2 pi I over 3, because these are both elements in this field. So here, sorry, when I wrote this is supposed to be a subfield of complex numbers. And so sort of this ambiguity sort of propagates into sort of an ambiguity in this statement here. And if there's, there's no ambiguity when there's sort of a unique root in this extension. If f has a unique root in this extension, then sort of, well, this map of fields has to send that root to that root. I mean, I guess maybe, yeah, so let me add this as a remark. I probably should have said this at some point before now, but I guess it fits here as well. So let me make this remark and then we'll take a quick break. So the remark is so if f is contained in, right, so this is any polynomial, and L over K is an extension, L1 and L2 over K are extensions. Then sort of any, sort of if I have a map, let me call it psi from L1 to L2, that restricts the identity. So I have a map of extensions. That's a map of fields that restricts the identity. Recall that a map of fields is injective. So this is sort of injection of fields that sort of restricts the identity on K. So any map of fields like this identity on K sends roots of F to roots of F. So roots of F in L1 to roots of F in L2. I mean, just the point is sort of if alpha contained L1 is a root, then of F, then let me write sort of F equal to A1, A0 plus A1x plus we have to ADX to the D for the AI containing K. Well, psi of F of alpha is just going to be psi of, I'll expand it, A0 plus A1 times alpha plus all the way up to AD times alpha to the D. Then, well, it's a field automorphism. So this is psi, and it's a map of fields. So this is psi, in particular, it's a map of rings. So I can sort of pull in applying psi through all the additions and multiplications. But now all of these coefficients are in K. And I know this map is the identity on K. That was my assumption. So that means like I haven't done anything to the coefficients. This is psi of alpha. So I ran out of space over here. I guess that's a pre-computers problem, but I'm not very good at this lasso tool yet. Okay, so psi of F of alpha is F of psi of alpha, is what we just showed. But so if F of alpha is equal to 0, then psi of F of alpha, then F of psi of alpha is psi of F of alpha is psi of 0 to 0. So this is sort of an important rigidity property to field, to maps of field extensions, is that sort of they have to send roots of a polynomial to roots of another polynomial. So this is somehow a map from K adjoint alpha to K adjoint beta is determined, well, not even just a map from K adjoint alpha is sort of completely determined by what it does on alpha. You can see that because a map from sort of K adjoint X is completely determined by what it does to X, as long as sort of we know that it fixes K. So it's completely determined what it is next. But on the other hand, like, I mean, well, it has to be sent to a root of, like, to factor through this guy, it has to be sent to, like, X has to be sent to a root of F. So this is sort of just, and what I wrote down here is sort of just another way to sort of make the same observation. And you could, yeah, let me not, probably I shouldn't belabor that point anymore. But let's take a pause here. We'll start again at 125. We'll get started again. So the next thing we want to do is just bootstrap this procedure up a little bit. So instead of just finding a single root of a polynomial, you might want to find all of the roots of a polynomial. I mean, and let me just point out that sentence doesn't make any sense. Like, in this context, like if I start with an irreducible polynomial, like in K of X, finding all of the roots of that polynomial is essentially a nonsense sentence because you have to say where those roots should live. Like if you want to find all of the roots of a polynomial, well, you need like, and I've already sort of made this big hullabaloo about how there's not like one extension, like one sort of universal extension that contains all field extensions. Like there's no, and sometimes there's no natural place to look for roots of this polynomial. So, I mean, you don't find all the roots of the polynomial. What you do is you construct some extension where sort of the polynomial factors into linear factors. And so sort of really when you say you want to, I would say I want to find all the roots of a polynomial, I mean, I want to sort of find some field extension where it has as many roots as I think it should, which it means sort of it factors into linear factors. So that's going to lead us to the topic of the splitting field, which is sort of slightly more specific. So if f is a polynomial, then an extension L over K is a splitting field for f if two things hold. So first, we need f factors into sort of degree 1 polynomials or linear factors in L brackets x. So I think of polynomial as a coefficient of L, then I can factor it into sort of linear factors. But I mean, that's, and then the second condition is that sort of L should be minimal for this. So, so if I take all the roots of f, which I should note, and if f has degree d, there will be fewer than d roots, but there might not be d roots. Like, and I'm not disallowing multiple roots here, so f might have multiple roots. But if alpha 1 through alpha s are the roots of f, no, s is less than or equal to the degree of f, then L is generated by those roots. So a splitting field is a field where the polynomial sort of has all of the roots you expect it to have. So it has sort of factors in degree 1 polynomials, and moreover, like it's sort of as small as possible. Like there's no subfield where that holds true. Okay, so then, I mean, the theorem where you bootstrap off the other one is splitting fields exist. So if I start with a polynomial, I can always find a field where I have all the roots and it's sort of as small as possible. So splitting fields exist. And sort of just like we had a uniqueness statement above for sort of the field for the smallest field that contained a root, here we have a uniqueness statement too. And so NE2 are isomorphic as extensions of K. So if you have two sort of a priori, and if you have two different splitting fields, well, you can always find an isomorphism of fields between them that acts as the identity on K. Okay, and so proof, I mean, so it suffices to just construct. So for existence, it suffices just to construct one. So you construct any field, an extension sort of satisfying part 1. So just construct any extension where sort of it has all of the roots it's supposed to have, where it factors in degree 1 polynomials. Then once you construct sort of any such extension, you can just take the smallest sub-extension generated by the roots. So like the only trick, and the only thing you need to show is that there is some field extension where you polynomial splits into linear factors. And so you sort of do the first part. And you can do it by induction, basically. So you induct on the degree. Well, you can always add one root. And if you add one root, that means you have to divide by a linear factor. And now you have some new polynomial, which is of lower degree. And then you can apply your inductive hypothesis. So you sort of get two extensions. So this is sort of something you can work out the details on your own. And then similarly, I mean, saying that they're unique up to isomorphic, that there's an isomorphism of these extensions of the K, like, I mean, you sort of, again, you use that sort of, if you add any single root, like you get isomorphic extensions, and then you sort of just bootstrap up from that. So you sort of have to bootstrap up on the same way. Okay, so that's the result. So splitting fields will be pretty important for us going on later. They're important in the study of Galois theory, or in the study of, and they're important in Galois theory. So we'll come back to this a bunch later. But let me sort of just keep on going on this same train. So I mean, we've seen that if we start with a polynomial, we can always find an extension where there's a root. Then now we've seen that, in fact, we can do one better. We can sort of find an extension where that polynomial has all of its roots. And I note, I didn't say this, but I note that by construction, this will be a finite extension because it's going to be finitely generated and algebraic. So this is a finite extension. I mean, maybe I should sort of say the following result because it'll be useful later. And it follows sort of from the way you prove it. But so you can think about this on your own. If sort of L over K is a splitting field for F, then the degree of L over K is at most sort of the degree of F factorial. And it just comes from, like, if you add one root, you get a sort of degree F extension. And like now you sort of divide by that root and like you get some new polynomial you're trying to add roots of, and sort of if that's irreducible, then sort of you get a d-1 degree extension, and then so you just multiply up the tower. Okay, so this is sort of useful to know. There are other ways to see this, and we'll talk about this again later too. Okay, but so that was a side note. You might ask, like, can you do this all at once? So the next question is like, given a field K, like, is there an extension L over K such that sort of any F containing K of X splits into linear factors in L brackets X. So I mean, this is this is almost, it's not obvious from the way I wrote it, but this is sort of ends up being equivalent to every polynomial has a root. Actually, sorry, I should probably be careful. Let me just say it like this. Okay, so, and the answer is, the answer is yes. So in such a, so theorem / definition. There is such an extension. And there exists such extension. Let me say, which is furthermore algebraic over K. And such an extension is unique up to isomorphism. So this is called so such an L would be called an algebraic closure. Okay. Okay, so again, the key step in sort of finding such a thing is not sort of the second part where you sort of have in the second condition sort of that it should be algebraic over K. Sort of you can, this is sort of easy to get once you have an extension where you have all of the splitting. So like, so how do you prove this? So first you construct an extension where all polynomials split. Then you show, well, in all of the roots of the polynomials are algebraic over K, but then you sort of show, but in the field itself, like might not be algebraic, but so you just show that the subfield, or that the subset of elements algebraic over K is a field. Okay, and that sort of gets you from sort of having an extension where everything splits to having an extension where everything splits and is algebraic over K. And then, I mean, somehow for the uniqueness, you just sort of build up from the sort of the splitting field uniqueness is one way to think of it. Think about it. Sort of now, sort of every you can sort of think of this big field as just being a union of sort of the splitting fields inside of it of every polynomial in K of X, and then sort of okay, so we can go from there. And this is sort of a little bit, there's something to do here, but this is the idea. So we won't finish this. I guess yeah, so we only have 5 minutes left. So let me sort of just come back to the first part and the third part next time. Let me do the second part now, and then sort of give you one example where you sort of are already done just using the second part. So for part 2, well, you just need to show, so we have some extension L over K. So then let me say this way. The claim is if you have an extension L over K, then sort of the subset, I'll just write L superscript alg. And this is sort of just all of the alpha and L such that alpha is algebraic over K. But this is a subfield. Okay. And so, and what do you need to check? Well, you just need to check e.g. if alpha plus beta is contained in sorry, alpha and beta are algebraic, then so is like alpha plus beta, alpha inverse, alpha times beta. So we should do constant multiplication by constants. I guess it's subfield, so fine. Alpha times beta, like minus beta, minus alpha. Okay, sorry. So you just need to check that sort of algebraic numbers are like algebraic elements are closed under these operations. And then just to point out, like it's not, depending on how you think about this, it's not so obvious. Like if I just give you, sorry, like if I just give you sort of f of alpha is equal to 0 and the polynomial such that g of beta is equal to 0, like it's not sort of, well, like it's not clear there exists an h such that h of alpha plus beta is equal to 0. I mean, like it's not like I can, like h of alpha plus beta is not, it's not h of alpha plus h of beta. Like, and like the relation between sort of, and when you evaluate, like these are really polynomials, so they don't satisfy like any natural linearity properties or anything. So it's not sort of not as simple just sort of combining these in some sort of naive way. And there is, you can write down sort of a procedure that would let you do this. So it's not sort of impossible, but it's sort of the hard way you could prove this. There's an easy way. Just note sort of alpha plus beta is contained in K adjoin alpha and beta. And so K adjoin alpha is contained in K adjoin alpha beta, K. Well, and this is a finite extension. And this is a finite extension. And so, sorry, this is a finite extension. And so their product is, and so they're, so this is a finite extension. And so these are both finite because they're algebraic and finally generated. They're generated by a single element. And let me say, and it's probably, that's a little bit dishonest. Let me say it this way. I mean, they're finite because each of them is obtained, like this extension, you're just adding the algebraic element alpha. So like, you know, sort of this has, the degree of this extension is the degree of the minimal polynomial of alpha. And here you're just adding in beta now. And while beta is algebraic over K, so in particular, it's also algebraic over K adjoin alpha. So again, sort of you're just like the degree is the degree of the minimal polynomial, now not over K, but over K adjoin alpha. But that's even better, sort of even smaller. And you actually see sort of K alpha beta, that the degree is sort of at most the product. Of the two degrees by that argument. And well, and but alpha plus beta, alpha beta, alpha inverse, and so on. Like they're all, all of these elements I said we had to check were algebraic are all contained in this finite extension. But a finite extension is algebraic. So these are sort of all algebraic because they're contained in this finite extension. So somehow the point is, and when you're only working with like a finite list of algebraic elements, you can sort of always be only working in a finite extension. This is, so even though like this whole extension, like L alg over K, like this whole sort of set of all algebraic numbers, like if L is an infinite extension, like this might not be, and this might be infinite over K, this L alg. But like if I'm only need to check something about if two elements, like those are all contained in some finite subextension. That's sort of the idea going on here. Okay, so example. The complex numbers are sorry, every polynomial in C of X splits by Liouville's theorem. So, and this is just the statement that the complex numbers are algebraically closed, but I haven't said what that means yet. So let me say it this way. So I don't know, you may or may not have seen this proof, but like there's a simple proof that's sort of a fun exercise if you've never seen it, that shows every polynomial over the complex numbers has a root, and therefore sort of splits by induction, splits into linear factors, just using Liouville's theorem, which is just a basic result in holomorphic function theory. And so, but now C over Q is a field extension. So if I sort of write Q bar, so it's sort of all of the algebraic elements in the complex numbers over Q. This is an algebraic closure of Q. So, I mean, the point here is like, if for a field that we already know how to put in the complex numbers, well, since like now you can get an algebraic closure out of it, you can get an algebraic closure of it just using the fact sort of that we know the algebraic numbers are algebraically closed, and using this result that sort of the subset of algebraically closed elements is algebraically closed. And of course, you can also give an, you can, and we'll see next time, you can sort of do an algebraic construction that works for any field. And you don't need, I mean, you can also sort of prove the complex numbers are algebraically closed without using Liouville's theorem. So then there are different ways you can go. This is sort of, well, okay, let me stop because it's over time, and I'll say more about this next time.